All right, welcome back, everyone. This is CS 480-680 Introduction to Machine Learning, as taught at the University of Waterloo in fall 2024. This is lecture 15, and today we're going to be talking about recurrent neural networks. Okay, so in the course so far, we've encountered several models that essentially allow us to move between vector spaces. So we first saw classification where our goal was to learn some approximation of a function f that would allow us to map from a fixed dimensional vector of some dimensionality d to either plus or minus one. This was the classification problem, specifically binary classification. And then regression, we were mapping from some vector from vectors of dimensionality d to somewhere on the real number line. And then recently we generalized this to multivariate regression to be able to map between vector spaces. And so critically, in each of these cases, we had a fixed size input. So we were receiving a single vector, and we were outputting a single item. And that single item was either an integer, a real number, or a real valued vector. These tools have been pretty powerful. They got us pretty far. But the models that we've encountered in this course so far can't explain a lot of the behavior of a lot of tools that we use every day. So for example, consider this prompt response interaction that I had with ChatGPT. So I asked it for a time travel story, and then the model generated this complete narrative, with some descriptive details, like it's in New York. There was a 28-year-old, had some character development, and it did this without knowing beforehand the length of the prompt I was going to give it, or how long its response would need to be able to provide a satisfying answer. So I didn't tell it how long the story should be. It had no idea how many words my prompt was going to be, and yet it was able to handle that fluidly. And so this ability to generate contextually coherent and engaging text, especially for this open-ended story task like this, it requires a model that can really go beyond those that can handle the fixed length inputs and outputs that we've been studying. And the GPT model actually, it has no idea what length of sequence prompt it would receive. And it also doesn't have any built-in understanding of how many words or sentences would make for a complete response. It dynamically generates the text one word or one token at a time, and conditions each word on the context of everything that came before it. Also had a bit of fun with ChatGPT to see if it would become self-aware and start talking about itself in this way, but it didn't have much luck there. Okay, so yeah, we can think of these sequential tasks, or tasks involving processing of sequences or a generation of sequences. We can think of them as falling into one of three categories, depending on the nature of the input and the nature of the output. And so one type involves learning a function that can map a vector to an arbitrary length sequence of vectors. And so this is called the vec-to-seq, or the one-to-many problem. And it's often represented. You might see it if you go online. You're reading blogs. You'll see it as like a single rectangle being mapped to multiple rectangles through some intermediate processing. And so, formally stated, vec-to-seq concerns learning a function parameterized by some parameters theta, where we're mapping a single vector in R to the D, where D represents the dimensionality of the input vector, to a potentially infinite length output sequence, each element of the sequence is in turn a vector that has its own dimension C. So yeah, the dimensionality of the input space is not doesn't dictate the dimensionality of the output space. So D and C are different. But the real thing to focus on is that we're learning a function that can go from a single vector to a potentially infinite sequence of vectors. And so why would we want that? And so this structure is useful, yeah, in real world applications where you need a fixed input is going to trigger a sequence. And so an example of this is image captioning. For example, as we saw in the lecture on convolutional neural networks, CNNs map an image to a vector in some high dimensional, semantically meaningful feature space. Um, and if we wanted to generate a caption of that image, the caption for that image could take on an arbitrary length. So, for example, this image here, the RNN felt that two sentences were needed to describe what's going on in the image. One focused on the group of people being at the outdoor market, and the other describing the vegetables and the fruits that were in the market itself. Another type of sequential processing problem is when we're given a variable length sequence and we need to learn a mapping to a single vector. So this is called the seek to vec or the many to one problem. So the model receives multiple vectors and it must output a single vector. So formally stated, this concerns learning some parameterized function that can map from R to the TD to R to the C. And so capital T now represents the length of the sequence or the maximum number of time steps. And as before, C represents the dimensionality of the output space as before. Tasks like sentiment analysis and document classification can fall under this category. So for example, if the model has to process some sequence of words in a movie review like this one from the IMDb database to find out the sentiment within this review, such as negative or positive. So, for example, this individual describes the film as being one of the worst of the 1990s, and throughout the whole review, this review was classified as negative. And then yes, and then yeah, another example. Talking about brilliant casting. Everyone's direction, everyone really suited the part they played. Amazing actor. Same director, came from the Scottish Island as myself, so I loved. And so yeah, this review here was classified as positive. And so yeah, the key difference here between the classifiers that we're dealing with now is that whereas unlike earlier models that we're handling fixed size inputs, the length of this review can change, right? So this review was longer than this one, so it's 6 lines rather than 5. And so this would make it challenging to try to directly specify the size of the input vector in advance. And so the model, instead the model adapts to varying sequence lengths while capturing the essential information from the entire input sequence. So technically this is we're not really mapping to a vector per se because we're mapping to in this case simply plus or minus 1 or it's a binary classification task. Either positive or negative sentiment. We could extend this though to a regression task where instead of a binary output, maybe the model produces continuous sentiment score and potentially map to a vector to characterize to create multiple scores, to assign scores along multiple dimensions. Finally, in the seek-to-seek problem, or the many-to-many problem, models have to generate a sequence of outputs that align with the structure and meaning of the input. So an example of many-to-many is a predictive text like autocompletion. So for example, after typing auto C, the system, Google's search engine suggested possible completions such as autocorrection, AutoCAD, autocratic leadership. Um, and so this input prompt, these five characters, were mapped to several possible sequences. So this sequence of characters here is we some length that's different from the length that went in, and each of these possibilities have a different length than the length that was set in. The Google search engine didn't know how many letters I was going to provide, and if I were to provide more letters, then it would change its suggestions. So each new character that gets typed in would be fed into the model, and the model is going to update its predictions accordingly. Another more challenging example of many-to-many is machine translation. And so because each word or phrase in the source language often corresponds to a sequence of words in the target language, the model has to capture both the mathematical structure as well as the context. For example, in this example, the model is trying to translate from French to English. It needs to produce coherent sentences that critically match the original input's meaning, while adhering to the target language's syntax. As an aside, Canada has some pretty excellent, as well as enormous data sets of documents in both French and English. So it's an ideal setting for training models in these machine translation tasks. Leveraging these data sets, seek-to-seek models can learn nuanced language pairs effectively, improving translation quality and capturing the subtleties of the language. And so machine translation models rely on this many-to-many structure to process languages where word order and meaning can vary significantly between the source and target sequences. So for example, in French, we can focus on this bug de l'an 2000, and that means the millennium bug. When they thought that rolling over from 1999 to the year 2000 was going to break everything. But critically, the l'an 2000, that means the year 2000. That just shows up as millennium bug. So we've got four words that went down that was translated to two, and then the order of those two output words has also changed. So now bug appears in the second, in the final position, whereas it started off the phrase in French, referring to the year 2000. That appeared at the end of this subsequence, whereas now it appears at the beginning of this subsequence. So in order to make an effective translation, you can't just go word by word. You do need to be able to take into account the context of the word in order to translate effectively. So today we're going to talk about one way to address these sequence modeling tasks, which is with recurrent neural networks, or RNNs. And so RNNs are a specialized family of neural networks designed specifically for processing sequential data. Um, it's really hard to understate or to overstate the diversity of architectures that are out there for RNNs. Um, it's really not like with convolutional neural networks where there was a strong correspondence between members of the same family. And yeah, there really are quite a few different architectures out there for different types of problems within the general umbrella of recurrent neural networks. And so, yeah, unlike traditional neural networks, which handle each input independently, RNNs have a unique architecture that allows them to maintain a form of memory over time. Um, so that this means that the output at any one time step, represented as y, it depends not only on the current input x, but also on this internal state h. That's going to evolve as the sequence progresses. And so why does that happen? Um, the hidden state, yeah, units in the hidden states are connected to each other as well. And so this hidden state sets RNNs apart from standard neural networks because they carry over a form of memory, and that enables them to keep track of sequential information over time. So yeah, this hidden state is crucial to RNN's function. It kind of acts like a latent summary of all the information that's been processed so far, to try to capture dependencies and patterns in the sequence that have accumulated over time. And then so the idea is that as each new input in the sequence is processed, this hidden state is going to get updated. And so this is going to allow the network to remember, for lack of a better word, at the risk of anthropomorphizing, allow the network to remember important features from previous steps. And so we call this type of processing in RNNs stateful. And it's highly effective for tasks where the context of previous inputs matters, especially for language modeling, where each word's meaning can depend on the words before it, or in time series analysis where patterns over time are really important. So yeah, essentially the update mechanism allows RNNs to capture dependencies over time. Yeah, yeah. And so yeah, just to summarize again, yeah, in an RNN, the units in the hidden layer are going to loop, they loop back on themselves. Yeah, each unit receives not only input from the input, but also passes information forward across time. And so yeah, this design allows RNNs to handle a variety of sequence-based tasks. So today we're just gonna scratch the surface of RNNs really. We'll be focusing on the sequence generation problem. First to formulate it as a probabilistic parameterized model. We're then gonna go into how those parameters are estimated, which are gonna reveal that RNNs are a bit of a double-edged sword. They've got they're theoretically powerful, but we're going to see that this can lead to some challenges in practice. We're then going to conclude by going over some other approaches to building recurrent neural networks that alleviate these issues or even sidestepping them entirely. Because like I said, RNNs are a very diverse collection of networks, all types of different architectures and ways to train them. And so for the first couple parts of this talk, we're going to focus on the standard story for recurrent neural networks, and then in the last part of the talk, we'll go over some alternative approaches that are still out there and respectable and yeah, followed in subcircles, but potentially not the mainstream story of recurrent neural networks. All right, so yeah, how can we formulate this sequence generation problem? So one way to model sequence generation is through a probabilistic approach. Um, so yeah, the key question we're really interested in is the probability of observing a sequence of targets, y sub 1 through capital T, given an input x. And so in this setup, yeah, y sub 1 through T, that's the sequence of targets, or yeah, the outputs that we would like to observe. Um, and then we're going from time step 1 to capital T, where T is uh, the maximum length of the sequence we're working with. And it's taken that this can be adjusted dynamically based on the task, this capital T. Um, and so yeah, then the model yeah takes into account an input variable x, and then we can interpret this as the external information that influences predictions across time steps. Um, our model, though, in an RNN, it's going to generate outputs through evolution of its hidden state, which we denote by H. And so we can analyze this effect of the hidden state by making use of that same trick we saw during the lecture on expectation maximization, of marginalizing overall possible hidden states. So yeah, since the hidden states are latent, we sum over all possible sequences of hidden states from the first to the capital Tth time step. And yeah, this summation is necessary because without directly observing the hidden states, we need to account for the possible configurations of these states to get the overall probability of the target sequence. And so, yeah, in other words, since the hidden states aren't directly observable, we account for all possible hidden configurations. Okay, and then so we can then expand this marginal probability by expressing it as a joint probability distribution of the output sequence and the hidden states. So this is, yeah, we can arrive at this by applying the chain rule of probability. And this allows us to break down, complex joint distribution into a product of conditional probabilities over time steps. In this case, we're saying that the probability of the entire sequence can be factored as a product of the probability of each output given its corresponding hidden state, multiplied by the probability of each hidden state based on the prior hidden states, previous outputs, and the input x. So this is a big break from how we've typically been dealing with these joint probabilities, especially with maximum likelihood estimation in the past. So in the past, we've been assuming independent samples to compose the joint distribution into a simple product of probability densities or probability masses. But here we're not making that assumption of independence. We're assuming instead that they depend on one another. So consecutive samples depend on one another. And so this requires that the joint distribution be decomposed into the product of conditional probabilities. And so crucially, this framework allows for dependencies across time steps. So that the model is going to capture the sequential nature of the data instead of assuming that each time step is independent. So yeah, we can also to give a little bit more intuition about this factorization here. So that this first part, this is the probability of each output given the hidden state. So this tells us how likely we are to observe a particular output at a given time step, given the internal state, the hidden state of the system at that time. And so yeah, there is a bit of a probabilistic decoupling going on here. So it says that the output yt isn't determined exactly by the hidden state. There is it's a probability of observing the output given the hidden state. And then the second part, this is the probability of the hidden state given the previous hidden state output and the input data. And so this represents the transition probability from a given state to the next. So yeah, putting it all together, we've got the probability of getting into a hidden state given that we were just at one. And then once we end up in that hidden state, what's the probability of observing a particular output? So this sequence model we want is called a conditional generative model for sequence generation. So conditional generative modeling is a framework commonly used in machine learning tasks for language modeling, where you're trying to predict a sequence of outputs based on input data. The model is designed to compute the probability of a target sequence given some input sequence. Yeah, so that was pretty abstract. To try to reinforce what we just formulated, let's consider a simple problem of generating a sequence of letters. So we can define the sequence we want to generate, which is hello. So the characters HELLO in that sequence to spell out the word hello. And to keep this example simple, let's assume a constrained alphabet consisting of only the letters H, E, L, and O. Our process is going to begin with the model receiving an initial input of H. And so this initial input provides the model with a kind of starting context, which it can use to predict the next character in the sequence. And so using this initial context, the model is going to generate a probability distribution over the next possible characters. And so this distribution of probability of y1, so the output at time step one, given the fact that the input was the character H. So this is a probability, the probability of each character in the alphabet following H. And so in this case, the probability, we would want a model where the probability distribution indicates a strong preference for the character E as the next character. So this is reflected by the fact that we've got this tall bar above E, and these ones are quite a bit shorter. So the model should select E most of the time and select H, L, and O not very much of the time. This suggests that based on the model's learned structure, E would be the most likely next character in the sequence after H. Cool, makes sense. And so once the model samples E as the first character in the generated sequence, it can then update its context and move on to predict the next character. And so the new context now includes both the initial input H and the newly generated character E. So if the model fed its output back into itself, then this updated context is going to allow the model to produce a probability distribution for the next character in the sequence. So this would be the probability of y2, given the fact that y1 was equal to E and x was equal to H. And so now what we would expect to see is that there would be a high probability assigned to the letter L. And so this indicates that given the context of H followed by E, the model finds L to be the most probable next character. Again, this probability distribution reflects the model's understanding of how sequences should unfold within this limited alphabet of 4 letters. So crucially, if we were to iterate this forward just one more step, the next letter that it would predict would also be L. And so this would be the first time where the model couldn't simply memorize an association between the current letter and the next one. And so it would have to make use of the history to disambiguate between, the L to L transition and then the L to O transition. Um, so yeah, so there is, so we really do need context in order to be able to predict uh, even predict the next character within a word. So to summarize, at each step, the model is going to take into account the current context, produce a probability distribution over possible next characters, and sample or select from the most probable one, and then feed that sample back into its own context. Okay, so let's now start thinking about how we can implement this in an RNN. So we can begin with initial hidden state H1 for for sequence generation. This initial state might be initialized as a kind of neutral starting point, like a vector of zeros, or could be based on some prior information depending on the specifics of the task. But most often we're just going to initialize that to zeros. And then using that initial hidden state, the model is going to generate a probability distribution for the first output y1 as before, and that's we can compute that through a function which I'll just call g for now. And so g is going to transform the hidden state into a probability mass function over y1. And so this is going to capture our uncertainty as well as our confidence for multiple possibilities for what that first output could be based on the context at the time. And then once we have this distribution, we can either sample from it or just choose the most likely output. And so this sample would be tilde y or y tilde. And then so after producing this first output, the model is then going to update its own internal state by applying some function f, which takes in the previous hidden state h1, the first output y1, and any additional input information x. And so with h2 established, the model is going to repeat the same process for generating the next output y2. It's going to compute a probability distribution for y2 given h2, again using that same function g, and sample or predict y2 accordingly. And so this process of updating the hidden state and and generating the outputs, we're going to continue that for each step in the sequence to allow the model to generate an entire sequence one step at a time. Where each time is conditioned on the updated hidden state. Okay, so what about those functions f and g? So a common choice to take the update function at f is the tan h function, and the tan h function applied to a weighted sum of the concatenated input vector, includes x and the previous output y, combined with the previous weighted hidden state ht, and an additional bias term. So w xh and whh, those are weights that allow us to move from the input to the hidden state, and then from map from the hidden state back to the hidden state whh. Tan h function maintains the hidden state values within a manageable range. So tan h has a range of -1 to 1. So this introduces that nonlinearity that we want to allow the model to capture more complex relationships in sequence data. These weights and this bias, those are going to be trainable parameters of our model. The function g, which we said is going to convert the hidden state into a probability distribution for sampling purposes. Because we're going to be working with a categorical distribution, or we're concerned with a categorical distribution in this case. we can apply the softmax to an affine transformation of the hidden state. And so these now W sub HY, that moves us from the space of the hidden state to the space of the output. And W sub H of Y and BY, those are also trainable in our model. So yeah, the softmax function, we can use the softmax function here. We can take the softmax function as G, and that's going to ensure that the output of G is at least a valid probability distribution, with the values that sum to 1 across all possible outcomes for each step. Yeah. Okay, so we've got a handle on the sequence generation problem and its high level behavior. We can now map this onto a recurrent neural network. So yeah, to summarize, the hidden state H of t, that's going to be computed by applying tan H function to the affine combination of the input, the previous state, and the bias. And yeah, X of t represents the input at time t, and for us that's going to be we've been concerned with this character level RNN of typing out the words, typing out hello. So in this case, that's going to be X of t is going to be a one-hot encoded vector of dimensionality corresponding to the total number of unique characters in the data set. The weight matrix W sub X of H, that's going to have dimensions to enable mapping the input vector into the hidden state space. And so that the hidden state space can be any dimensionality you want. That is not constrained to be the dimensionality of the input or the output. And then W sub HH, that's the recurrent weight matrix with dimensions corresponding to the dimensionality of the hidden state that we selected. And then given this, we're going to generate the pre-activations YT using the affine function of the using an affine function of the current hidden state, and where W sub HY is gonna be able to map us from the hidden state back into the output space of character probabilities, and then BY is a bias vector. And so for our character level RNN model, this vector of pre-activations, that's going to have the same dimensions as the size of our vocabulary, and then where each element of this vector represents an unnormalized logit score for each possible character. And then given these pre-activations or logits, we're going to pass these through a softmax function to produce a probability distribution over all possible characters. And so this is going to be the model's predicted probability of character of some character, I being the next in the sequence. And then we'll sample from that categorical distribution to get our next sample. To train the model, we're going to define a loss function to measure the difference between the predicted distribution p sub t and the actual target character distribution. And so this loss, we're going to compute that at each time step as the negative log of probability distribution at the target where this target is the index of the actual next character. And so the total loss L is gonna be the sum of these individual time step losses over the entire sequence. And so this is going to encourage the model to increase the probability of the correct next character. Yeah, we're going to compute these gradients of the loss with respect to each of the weight matrices. So W sub XH, W sub HH, W sub HY, and then the two bias terms. Um, and then we're going to adjust these parameters in a direction that would minimize this loss. But then at test time, the RNN is going to generate text by feeding in an initial character and sampling from the predicted character probabilities to choose the next character. At test time, the RNN is going to generate text by feeding in an initial character and sampling from the predicted character probabilities to choose the next character. And that chosen character is then going to be fed back as input to generate the next character distribution. And then the process is going to continue to be able to sample a complete text sequence. Okay, so we've talked about the basic architecture of an RNN. Let's now think about how we can actually optimize the parameters and make this model actually useful for each sequence generation. Okay, so the diagram on the left here, this shows a compact representation of an RNN. So at each time step, the input vector x is passed into the network where it gets mapped into the hidden state through that weight matrix W sub xh. And yeah, at this point, this is where we would apply a nonlinearity, just like we do with neural networks. We've been talking about the tanh function in this case. And then from this hidden state, we're going to decode an output O using another weight matrix W sub HO. And then to train this model, we can compute the loss by comparing O to the target Y. So for example, in this character level RNN, the target could be a one hot encoded character. And yeah, so hopefully this feels familiar. This is, the setup is basically like a standard feed forward network. We know how to train these kinds of networks using gradient descent in the training goal. So specifically going from the input through the hidden state through the output. That part, this forward part is familiar. But of course, our RNNs aren't just feed forward networks. And what makes them different is this feedback connection in the hidden layer, which is controlled by the weight matrix W sub HH. And so this feedback means that the activations in the hidden state at one time step, they're not influenced just by the current input, but also by previous hidden state, by the previous hidden state from the last time step. And so yeah, this is what gives the network that kind of memory to allow it to carry information forward as it processes the sequence. But these recurrent weights, they're also learnable parameters. And what should they be such that we can make the most accurate predictions for the target Y. So to address this question, of how to figure out what those weights should be, those recurrent weights should be, we can actually change the way we think about the effect of recurrent connections by doing something called unrolling it in time. And so the unrolled view gives us this picture on the right. So when we unroll an RNN, what we end up with is essentially we're working with a sequence of feed forward networks, and one for each time step. So an input vector at time step 1, that's going to flow through the hidden layer to produce an output at time step 1 that we can compare to the target at time step 1. But this sequence of networks has a special property that the hidden state at one time step is connected to the next via by means of the recurrent weights W sub HH. So this is this is kind of like a kind of weight sharing, similar to what we saw with convolutional neural networks, to be able to implement a kernel and apply it uniformly over a whole image. Um, but what this means functionally is that the hidden state is going to accumulate a history of everything the network has seen up to a given point, or some notion of history of everything that has been seen up to that point. So this is going to allow a recurrent neural network to, use context from earlier in the sequence to make predictions later on. But when we train this network, we're going to compute the loss over the whole sequence of prediction target pairs, not just at one time step. Um, and so yeah, this is what makes RNNs effective, because they're going to be able to learn patterns that unfold over time, whether it's predicting the next character in a string, or modeling time series data, um, generating text. Because the activations carry this context forward, the network is going to be able to capture long-term dependencies in the data, which is pretty critical for many real-world applications. So this is unrolling. Yeah, we change the way we look at an RNN in order to compute the loss over sequence. We're going to sum up all the individual losses between the prediction and the targets. Okay, so with that view of unrolling the network in our minds, how can we compute the gradients with respect to the loss? So let's yeah, we can approach this with maximum likelihood estimation, or MLE, that as we've done before. So as usual, the goal, our goal is to find the parameters theta that maximize the probability of the target sequence of outputs, given the input sequence and the model parameters. And so in this context, Y represents the true target labels at each time step, and capital T is the length of the sequence we're working with. And so at each time step, the RNN is going to compute two quantities, or two key quantities. So first is the hidden state, and so we know that depends on the current input X and the previous hidden state, and yeah, some weights, the recurrent weights, WH. And so yeah, and then F, we'll just take that to be a differentiable function, like a combination of matrix operations and a nonlinearity like tan H. And then second, the network is going to produce an output, which is computed as a function of the hidden state, using another set of weights W sub O. So yeah, these two equations, they essentially describe the forward pass of an RNN, essentially how it processes the inputs and updates the hidden state to produce outputs one step at a time. Yes. Okay. Right. So to improve the model, though, we need to define and minimize a loss function to measure the error between the predicted outputs and the true labels, or the predicted outputs and the true labels, or the true targets. So we'll just call this loss capital L. We'll be general about what exactly this objective is for now. And also we do know how to compute the gradients with respect to the output, as well as the gradients with respect to the output weights. So we don't we can skip over those steps here, because we've done that before when we were talking about MLPs. But what is new now is the gradients with respect to these hidden weights, so the recurrent weights. So we'll focus our attention there. Um, so yeah, we're interested in the gradient of the derivative of the loss with respect to these recurrent weights. And so we know that this is going to be the gradient of the loss, which is gonna take in general the target and the output of our model at time step t. And we're going to be differentiating that with respect to the weights on the recurrent weights W sub h. And we're interested in summing up all of this over yeah, summing these gradients over the entire sequence. So from t equals 1 to capital T. And so we yeah, evaluating this derivative is going to require us to apply the chain rule. So we first need to compute the partial derivative of the loss with respect to the output at each time step. This is so yeah, to take us from the loss to the output. And so this is going to be pretty easy because it's it's just local to each time step. And then the second part, we're interested in the derivative of the output with respect to the hidden state. So this is it involves tracking the effect of the hidden state on the output. Is also pretty easy because it also only depends on the current time step. But the challenging part is this. There's a this third part here is tricky. So this is the derivative of the hidden state with respect to the recurrent weights W sub h. And so yeah, why is that tricky? So yeah, if we consider this this unrolled a subset of the enrolled view of the diagram that we had before, where the sequence consists of just three time steps, and yeah, time step 1, 2, and 3. If we're yeah, for the sake of argument, let's suppose that we're working with mean squared loss and scalar valued outputs and targets. And at some gradient descent iteration, our prediction for O2 is slightly less than Y2, slightly less than it should be. And so backpropagating this loss we would want to increase H2 because H2 directly influence O2 since through the matrix W sub HO. And yeah, to do this, to be able to increase H2, we would want to adjust the recurrent weights. We would need to adjust W sub HH, which governs the recurrent feedback connections of H1 through H2. But in so doing, by increasing H2 to try to improve O2, we're also affecting H3 because H3 depends on H2 through the same shared weights W sub HH. And so this means that any change to W sub HH for the sake of improving O2 is also going to indirectly impact H3. And so, yeah, and then moreover, because H2 is itself influenced by H1, which depends on X1 and the initialization of the hidden layer. So yeah, even in this relatively short sequence, yeah, to adjust W sub H, we actually need to account for the fact that it impacts all three hidden states and their corresponding outputs. And so in this three-step sequence, backpropagating the loss means computing how the gradients are going to flow backwards from O3 to O2 and O1 through the connections governed by the recurrent weights. Um, and so yeah, to compute the gradients of the loss with respect to W sub H, we're going to have to apply the chain rule iteratively across these time steps. And yeah, specifically adjustments to W sub H for improving O2, we need to account for how H2 is going to influence H3 via W sub HH. And then how H1 contributes to both H2 and H3. So can we actually compute this derivative of the hidden state with respect to the recurrent weights? So we do know that the hidden state at time step t is a function of both the recurrent weights and the hidden state at the previous time step. We also know that the previous hidden state, this itself is also a function of W sub h by the same logic. So direct application of the chain rule to this function of multiple variables, that's going to give us this expression here. And so we can interpret this result as splitting up the derivative of h of t with respect to W sub h into two terms. So this first term is going to capture the direct contribution of how changes in W sub h affect h of t through the function f directly. And then this second term, that's going to count for how W sub h affects h of t indirectly through its effect on h of t minus 1. Now, since the partial derivative of h of t minus 1 has with respect to W sub h, this has the same structure as the partial derivative of h of t with respect to W sub h. We can recursively apply this relationship to consider contributions from hidden states earlier, earlier and earlier in the sequence. And so we can, the compact expression, compact way to express this is as a sum of products. And so that, the summation over I is going to, that accounts for the contributions of hidden states from the first time step up to the one in question. And then this product term, that's going to accumulate the effects of intermediate time steps, specifically j equals I plus 1 to t. And so this is going to capture how a perturbation in W sub h is going to propagate forward through all intermediate hidden states. A few comments about this result. This process of unrolling the gradient across time steps is known as a back propagation through time, or BPTT. And so what we've done here is systematically apply the chain rule backward through the sequence to allow the network to adjust weights based on the cumulative effect of prior time steps. This hints at the couple, kind of a double-edged sword for RNNs. On the one hand, they're theoretically powerful. So the summation and this product term in the expression for the gradient, it demonstrates that the gradients are computed over the entire input sequence. So it takes into account dependencies that can span multiple time steps. Theoretically, this positions RNNs to propagate information through time, to learn long-range dependencies in sequential data. This will make them a powerful tool for problems like language modeling, time series forecasting, speech recognition, things of that nature. But it also suggests some issues we could run into while training. So this product term, for example, this involves repeated multiplications of gradients across time steps. And so if the gradients of the activation function, like TNH, if they were smaller than one, these products are going to shrink exponentially as we increase the number of time steps. So this is going to give us this is going to result in the phenomenon of vanishing gradients, where the contributions of earlier time steps becomes negligible. And as a consequence, the network is going to have a hard time learning those long-range dependencies because the signal from some distant state in the past can't effectively propagate to the present. And so this is a problem in applications where capturing dependencies across long sequences is essential, such as understanding context, in a long passage of text. On the other hand, if these gradients are larger than one, then repeated multiplication is going to amplify them. And so this is going to give us the other problem of exploding gradients, which can cause instability during training, preventing the model from converging, but also resulting in poor generalization to unseen data, because a small change in the input could lead to a very large change in behavior. Um, yeah, so and then additionally, performing this full back propagation through time, as we call it, this is computationally expensive because it requires unrolling the entire sequence during the backward pass, and also storing intermediate activations for every time step in memory. And so this makes training computationally difficult for long sequences. And this further complicates the issue of long range dependencies because it's going to cost a lot in compute in order to get that. So in practice, therefore, we don't often do this full, or we don't often do back propagation through time over the full sequence. What happens instead is something called truncated BPTT. And so full BPTT takes into account a full sequence like this unbroken arrow here. Truncated BPTT is going to compute a sequence. It's going to do a sequence of backpropagation through time. So going to truncate the sequence a number of times and do gradients a few times over that sequence. And so we limit backpropagation to a fixed number of recent time steps rather than the entire sequence. And so we approximate the gradient and focus on short-term dependencies. Another approach is called randomized truncated BPTT. And here we vary the segment length randomly. And so, this is represented in this last line here, where the segment lengths used for gradients vary. So we've got some long ones, some short ones, some medium-sized ones. And then the motivation of randomized truncated BPTT is to have both short-term and long-term dependencies. And so while this approach is theoretically appealing, it hasn't demonstrated significant improvements over standard truncation in practice. We won't get into the reasons for this, but regular truncated BPTT is the default choice, as it strikes this balance between computational feasibility and the effective gradient estimation for training recurrent neural networks. All right, so we've specified the recurrent neural network model for sequence generation, gone over how backpropagation happens. Just to reinforce what it is that we're doing, or to bring this back to the character level RNN that we've been taking as the example in this lecture so far. This picture here provides a numerical example of what's going on in the hood. It was taken from a blog post by Andrei Karpathy called the Unreasonable Effectiveness of RNNs. And in it, he provided some some sample code to implement a vanilla or a character level RNN using the techniques that we've been talking about in this lecture. Yeah, we have an RNN with a four-dimensional input as well as a four-dimensional output layer, and then the hidden layer contains three neurons. And so each row represents the network's processing as at a given time step, with the flow going from the bottom and the input to the top layer. So the process is going to start at the input layer where each character is one hot encoded. And so this encoding flows through W sub XH to produce the activations in the hidden layer, where the RNN also incorporates information from the previous hidden state through means of the recurrent matrix W sub HH. So for example, at time step 2, the hidden state depends on the input as well as the previous hidden state. The hidden layer then connects to the output layer through W sub HY, which generates the logits for each possible next character in the sequence. So these logits indicate can be transformed into probabilities through the softmax function, but they indicate they correspond to how strongly the model believes each possible character is the next one. So, for example, in the first time step, when the input character is H, the model assigns a confidence of 1.0 to H. So we know that H is one hot encoded. So each character is one hot encoded, with H taking the first position, E taking the second position, L taking the third position, and O would take the fourth position. In the first time step, when the input is H, so we've got 1 0 0 0, the model's going to assign a confidence of 1 to H, confidence of 2.2 to E, -3.0 to L, and then 4.1 to O. The target character that we actually want in bolded in green, that's actually E. We can see that it's got a lower confidence than O. So the model is going to output O most likely, but we want it to be more confident in E. And so we would want to increase the confidence for E while reducing the confidence for the other characters in red. And so it's these, so we would want to update W sub HY, W sub HH, and W sub XH to be able to change these confidences accordingly. So I went ahead and played around with the code on Andre Karpathy's website to see how the character level RNN performs on different data sets, and observe that the kinds of sequences it produces. And so the training sequence I gave it was this. So this was a sentence that was taken from Andre Karpathy's blog. And what he claimed was that a glaring limitation of vanilla neural networks and also convolutional neural networks is that their API is too constrained. They accept a fixed size vector as input, e.g. an image, and produce a fixed size vector as output, e.g. probabilities of different classes. All right, so after at iteration 0, where we're just sampling the initial state has been cleared, and we haven't learned very good conditional probabilities for the context to the output either. And so at iteration 0, the output's pretty nonsensical. It's got random sequences of characters and symbols. Yeah, this is expected because the RNN hasn't yet learned any kind of meaningful patterns at all. Also, the loss is pretty high, so we're sitting just shy of 90. So this indicates at least a gap between the generated text or the text that the model spat out, as well as the actual target text. As we move to iteration 500, the model starts to produce sequences that resemble the length of words. So it started to intermix, introduce spaces at some, yeah, there's a few more spaces than there used to be, and they're appearing in places that we would expect words to be separated. Um, so it suggests that potentially by this point the RNN is beginning to learn some statistical properties of text, like these aren't real words anymore, but potentially there's some common letter pairs that are getting associated, like ed and um, uh, I and e. Yeah, but it's still far from capturing the full structure of the training data. By iteration 2500, the generated text is now actually pretty close to how English works. So now we can see several recognizable words and phrases. Um, so yeah, the uh, we can see glaring, limitation, vanilla. Almost all of this is pretty close to the training data. It starts to get a bit worse as we go longer into the sentence. Um, and then the loss has also dropped quite a bit from the original 80 and at iteration 500 down to 13 at iteration 2500. Finally, by iteration 10,000, the output is almost identical to the original training text. So the RNN has effectively learned the character level patterns and has produced coherent text that closely matches the structure and the content of the input. And yeah, this was trained using truncated back propagation through time with a sequence length of maximum number of time steps of 25. And so yeah, the RNN adjusted its weights over multiple iterations to produce increasingly accurate predictions for the text. But yeah, what are the limitations of this character level RNN? And so we can consider a slightly more confusing example. And so in this case, the training data uh, was a sentence with a fairly complicated structure. So if training vanilla neural nets is optimization over functions, training recurrent nets is optimization over programs. So sentence was again taken from Andre Karpathy's excellent blog post on RNNs. And so this sentence is tricky because it introduces dependencies across the different clauses that require the model to retain information over a longer range. And so we might expect this to be more challenging for an RNN, especially with the truncated back propagation through time that we're working with. And so at iteration 100, the output's pretty random, no meaningful structure here. Was expected in the early stages of training. By iteration 1000, the model has begun to capture some word-like structures, but there's a couple tricky things here, but at this point, not doing too bad a job. But even after 10,000 iterations, the model has gotten it's producing coherent input, coherent output, but it hasn't perfectly captured the original sentence. Um, so yeah, we've got everything up until this point. So if training vanilla neural nets is optimization over functions, training recurrent neural nets is optimization over functions. So it has missed this part here, optimization over programs versus optimization over functions. And so this behavior is indicative of a limitation of character level RNNs trained with truncated BPTT, is that they're going to struggle with these long range dependencies because the truncated approach prevents them from fully learning the relationships over extended sequences. And so this difficulty arises because each truncated segment is going to limit the influence of far off characters or words. It's going to make it difficult for the RNN to maintain context for a complex structured text that really does require remembering earlier parts of the sequence. Okay, so given these issues that we've seen training RNNs with truncated BPCT, are there other ways to build this kind of network? I mentioned in the introduction that RNNs are a very diverse family, and so what other ways are there to build an RNN? Specifically, can we structure a recurrent neural network to handle long-range dependencies more effectively? So this is precisely what the long short-term memory, or LSTM network, was designed to achieve. And so while standard RNNs struggle with long-range dependencies due to the vanishing gradient problem, the long short-term memory has a different kind of cell, and introduces a special mechanism for retaining important features over extended periods. So this figure here defines is a depiction of the LSTM, a single LSTM memory cell. And so in an LSTM, there's three, we handle three key pieces of information at each time step. So there's the current input, xt, the previous hidden state, h of t minus 1, and the previous cell state, c of t minus 1. So this cell state c, that's unique to the LSTM. And it provides the idea is to provide it with a long-term memory pathway that's distinct from the hidden state. And so unlike the standard RNN, the LSTM also introduces multiple gates that kind of act as self-filters to control what information to keep, add, or discard in the state, the memory cell state. And so each of these gates is represented with these sigma symbols. These denote actually sigmoid activations that output values between 0 and 1 to give the network a kind of fine-grained control over information flow rather than a simple keep or discard decision. Okay, so what are these gates? So there's a forget gate, which determines how much of the previous cell state to retain. And so this allows the LSTM to decide which past information is less relevant. And so values, if this gate outputs values close to 0, that's going to indicate forgetting. But then values near 1 are going to signify retaining information. And so, while the forget gate, it's important to note that while these gates are arranged from left to right, forget gate doesn't, technically operate first. It filters past cell state values before they're combined with new information. The input gate that manages the flow of new information into the cell. And so this gate doesn't control the raw input directly, but instead gates a candidate cell state, C tilde. And so this represents potential new information created by applying a TNH activation to a weighted combination of the current input and the previous hidden state. And yeah, so this candidate state that provides the new information the network might want to add to its memory. The input gates values also range from 0 to 1 to balance how much of this candidate is incorporated into the cell state. To kind of blend fresh data with the existing cell state memory. And then finally, the output gate that controls how much of the updated cell state influences the hidden state output at the current time step. And so after updating the cell state, the LSTM is going to filter it through a TNH function, and then modulate it with the output gate. And so this is going to produce the next hidden state, which serves as both the output of the LSTM for this time step, and as a short-term memory for the next time step in the sequence. And so the idea is that together these gates enable the LSTM to retain useful long-term information in the cell state, while adjusting the hidden state output according to the current context. And so the idea is that this balance between cell state memory and the hidden state's current context allows the LSTM to capture complex dependencies across sequences. And an LSTM is also trained using backpropagation through time, so the network's going to be able to learn weights for each gate to be able to control the information flow to capture both short-term and long-term patterns in the data. The gated recurrent unit, or GRU, this is an alternative to the long short-term memory. And it's designed to capture long-range dependencies in sequential data as well. And so, while both the GRU and LSTM are types of recurrent neural networks capable of handling temporal patterns, the GRU has a bit more of a streamlined architecture, which can make it a bit more computationally efficient. And so, unlike the LSTM, which has 4 gates to control information flow, the GRU just has two main gates. So there's a reset gate, and then there's an update gate. And so between these 2 gates, that it allows the GRU to decide what information to keep, what to reset, and what to pass on to the next step. So the reset gate determines how much of the previous hidden state should influence the candidate hidden state for the current step. And so it kind of acts as a selective filter, allowing the GRU to forget irrelevant parts of past information and focus more on recent inputs. So let's notice that the current input and the previous hidden state, they both pass through the reset gate. This also uses a sigmoid activation to produce values between 0 and 1, and that value controls how much of the previous hidden state is considered in the computation of the candidate hidden state. And then the update gate, it then determines the mix between the previous hidden state and the candidate hidden state. When forming the current hidden state. And so it combines information from the current input and the previous hidden state. So previous hidden state and current input, so they're both going to the update gate, and then applies a sigmoid activation function to produce values between 0 and 1. And so the idea is that by modulating the candidate and the previous hidden state, the update gate is going to enable the GRU to selectively remember useful past information or to incorporate fresh data to try and achieve a balance between memory and adaptability. So the final hidden state, that's calculated by blending the previous hidden state, blending the previous hidden state and the candidate hidden state according to the update gates function. Update gates output. So the update gates value is close to 1. More of the previous hidden state is going to be retained, similar to the short-term memory that we saw before. But if it's close to 0, then the candidate hidden state is going to take precedence. So it's going to allow the network to incorporate new information. So this streamlined approach gives the GRUs a flexibility that's similar to LSCMs, but it's a little bit simpler. Yeah, we've got fewer gates and therefore fewer parameters. So this makes GRUs a popular choice in practical applications, especially when efficiency is a priority. Yeah, one of the recurring themes, though, is that we've seen that learning weights in recurrent neural networks can be difficult, lead to various problems like the instability and the vanishing gradient problem. A clever approach developed in the earlier 2000s, it bypasses learning recurrent weights entirely. And so this, in a reservoir computer, we don't train the internal recurrent weights. Instead, what we do is we create an ensemble of neurons with sparse random interconnections, which we call the reservoir. And these random recurrent connections, they allow the reservoir to generate complex temporal patterns of the input over time. So it's going to generate a diverse set of random temporal features. And so these features, which emerge from the reservoir's inherent dynamics, are then used by a simple readout layer to perform tasks like classification or regression. And so only this output layer of weights is trained. And so this dramatically simplifies the training process since we avoid learning the recurrent connections. Of course, in order to make this work effectively, we need to select these weights carefully to ensure that the system is stable, that it doesn't blow up. Specifically, we aim for the reservoir's dynamics to be sensitive to inputs without diverging to chaotic behavior or vanishing to 0. A common approach is to set the eigenvalues of the weight matrix to be close to 1 so that the system is going to respond to inputs with a memory of past states, but gradually decay to 0 if those inputs were to cease. So this combination of stability or rich, rich temporal features constrained to be stable is what allows the reservoir computer to capture temporal dependencies effectively while keeping training computationally feasible. There's two main kinds of reservoir computers. There's the echo state network and the liquid state machine. Echo state network uses real valued neurons and enforces stability by controlling something called the spectral radius, which is the largest absolute eigenvalue in the recurrent weight matrix. And then liquid state machines use spiking neurons to create binary activations that respond in a stable yet dynamic way. But yeah, both methods rely on the reservoir's stable recurrent connections to transform the input into a set of temporal features. And a well-constructed reservoir with stable dynamics can generate a wide variety of such features to allow a simple output layer to learn combinations for final predictions. Another way to avoid training recurrent connections is to actually design them to solve a slightly different but related subproblem of of optimally representing a window of history of input. And so to that end, Volcker and colleagues, I included a reference in the next slide. They built on principles from control theory to actually mathematically specify the recurrent weights to maintain a memory over a predefined period. Specifically, what they did was figure out how to approximate a pure delay of some length theta. And so in the Laplace domain, a pure delay is given by exponentiating theta and then the Laplace variable s. And so while it's impossible to implement a pure delay in practice, it can be approximated up to some arbitrary degree of precision using a window of history of length theta. And so what they did was they showed that this is possible, by defining a linear dynamical system with a state vector m that evolves according to a state matrix A, which specifies the relationships between different components of the memory, and a matrix B that tells us how the input signal then influences that memory directly. These equations down here, they define how matrices A and B are constructed. But the key takeaway is that they maintain the historical information, or they allow the historical information to be maintained in an optimal way, which means that the memory is structured such that it captures the past with minimal redundancy. So what do the elements of the memory vector in a Legendre memory unit represent? And so the backbone of the memory system is something called Legendre polynomials, and they're sketched out here on the right. And so these polynomials they act as a set of basis functions to encode the input history over a rolling window. And so each of these curves, they correspond to a specific mode or level of detail in capturing patterns of the input signal within that window of history of length theta. And so the lower order polynomials, they're going to capture smooth trends like the signal's mean for I of 0, or ramping behavior for when I is 1. And then the higher polynomials, they're going to oscillate more rapidly. And this is going to allow encoding of finer grained fluctuations in the signal over time. And so crucially, the analysis showed that you can reconstruct the original signal U delayed by theta through a weighted or delayed by some theta prime, which is less than theta, through a weighted combination of the elements of the memory vector M. And so these weights are determined by this down here. But by extension, you can decode other functions from the historical window using this compressed representation of the window of history. The idea is that by projecting the history of a signal onto these set of basis functions formed by the Legendre polynomials, the Legendre basis provides a unique and optimal decomposition of the actual input of the original input signal. This rolling window approximation using Legendre polynomials was then applied to design a new memory cell for use in recurrent neural networks. The architecture they proposed is on the left here, and then the idea, the LMU layers, they call it the Legendre memory unit, dynamically combines the hidden state vector and the memory vector. I'm not gonna get into the details here because it's still non-standard compared to the LSTM and the GRU. But there are some promising results that indicate that the LMU is performs favorably compared to the LSTM. So these curves here compare the performance of the LSTM or of the LMU to the traditional LSTM on a memory capacity task. So that the task is designed to evaluate how well a network can remember information over a long sequence. And so what we can see is that the LMU consistently performs better than the LSTM across various various delay lengths. So it maintains low mean squared error even as the delay length increases. And so this indicates that the LMU can remember information for significantly longer periods than the LSTM without requiring additional training or tuning. It manages that by creating that compressed continuous time representation of the input signal, making it especially useful for tasks that require extended. Okay, so that brings us to the end of the lecture. Quick recap on what we covered. Yeah, we talked about backpropagation through time, and we went over how it relates to training a recurrent neural network in most cases. We also went over the details of building a character level RNN for sequence generation tasks. We also talked about a few other approaches to building a recurrent neural network that alleviate or avoid issues with doing backpropagation through time. So those are the two types of echo state networks, as well as decomposing into the Legendre basis, or to optimally represent some window of history, a rolling window of history. And then we also went over the architecture of an LSTM and the GRU memory cell. So hopefully, hopefully by now you feel comfortable to label the components of such a cell, and also explain their role with reference to the hidden state or the internal cell state. All right, so we'll see you back here next time when we'll be talking about tension mechanisms.